Okay, hopefully this will be a pretty short video. This is one of those things that you may want to pause and try to do it on your own because you only get to kind of see the neatness of this once. So, the question here is the square root of 2 a rational number? So we've talked about how to compute it. It's a process. Basically you take a guess, then you compute 2 divided by that guess, and then you average your guess with that 2 divided by the guess, and that's your next guess. And you keep doing that, and very soon you get a very good approximation of the square root of 2. That doesn't tell you whether it's a rational number or not, basically because at some point maybe the pattern will repeat itself, right? And we don't know. How do we approach this? Well, what would it mean to be for the square root of 2? So if yes, then the square root of 2 would equal to p over q, where p and q are natural numbers. Now, what do we know about rational numbers? Well, this is something that needs to be proved, but argued for, whatever. But basically, we can assume p and q have no common factors. So this is basically saying, so like if it was like 6/12, right? That's the same as, well, this is 2 times 3, and this is 4 times 3. So that's 2 divided by 4, and 2 is, of course, 2 over 2. So this is just 1/2, right? So we assume that it's of the form, the 1/2, so reduced form. So even if, so if you say square root of 2 is this rational number and it was not reduced, we reduce it. The fact that there's a unique, an existing reduced form of that number, that's a little bit deep, but that seems reasonable to accept at this stage, right? I'm not worried about it. You like it's good to contrast, like, is square root of 2 a rational number or not, right? Like, I don't know a priori if that's true or not. We're actually trying to figure out, this is proof to establish something that I don't know, versus the reduced form, where it's more like, well, how does that work, right? I don't know. But it's almost common knowledge, right? You know what to do. You factor these things into their prime factorization. You cancel things. That prime factorization is unique. Again, something that exists. Something, again, that one needs to argue. That's all. That's math nitpickiness. The core of the thing is square root of 2 equals a reduced fraction p over q. All right. So what does this mean? Well, that means that 2 is equal to p squared over q squared. Well, more or less, that would tell you that p squared is 2 and q squared is 1. But that's a little bit something to say. So 2 times q squared is equal to p squared. That's what that's equivalent to, right? So now we have a product, 2 times q squared, and we've got p squared. So 2 divides p. 2 divides p. Namely, p is equal to 2 times some other number r. So p squared is equal to 4r squared. And so we have 2q squared equals p squared. And then we have, this is equal to 4r squared. And so we have 2, sorry. So now we can cancel that 2. We've got q squared is equal to 2r squared. So now, so that implies that q is equal to 2s. All right? And so 2s squared is equal to 2r squared. And you get 4s squared equals 2r squared, or 2s squared is equal to r squared. And you just kind of keep repeating. So they're both sort of infinitely many 2's. Many 2's. Silly. So that doesn't work. Also, P and Q, no common factors. And this is kind of like P squared equals 2, Q squared equals 1. That's all the mantra. So that's basically the problem with the square root of 2 being rational, is it just doesn't work. If you do assume it, you assume the thing is in reduced form, you end up having both of them having factors of 2, so that's a contradiction. Bad. If you aren't really assuming reduced form, you get this infinite sequence of 2's, so they have like infinitely many factors of 2, which is kind of silly. And in fact, you could probably argue that if they're natural numbers, I mean, yeah, that they would get very large, infinitely large. So things break down basically. So square root 2 is not rational. All right, and that's that. So yeah, you can't write square root 2 as an exact form as a fraction. Certainly can't write it in an exact form as a finite decimal. And so to really write down the square root of 2 in decimal form, you would need to write down an infinite number of digits. Good luck with that. But again, it doesn't really matter. Whatever you're using the square root of 2 for, you can either use it in this exact form, because you're going to do further things like squaring or whatever, multiplying these things, and it just kind of goes along for the ride. Computer algebra systems are really great for dealing with those things. Or you approximate it with a decimal, and it's fine. You can use 8, 10 decimal places, and I'm sure that is far more precision than you will ever need for these numbers. All right, so that's the square root of 2 being irrational.